Welcome to the Porous Media Tea Time Talks. With this seminar, we want to give junior researchers working on porous media the chance to present their work to the scientific community around the world. This is meant complementary to the Geoscience and Geoenergy webinar, which you can find in our featured channels, as well as the Interpol webinars and the Interpol YouTube channel. I am Maya, and I'm here today with Catrin, Aryan, and Kamal. The first speaker today is Deepshikha Singh. She is pursuing a PhD in the Department of Chemical Engineering at the Indian Institute of Technology in Delhi. Her research is on multi-phase flow in porous media, with a special focus on large-scale wettability quantification. Deepshikha, you have already a first comment by Sunil Kumar, and I actually would like to invite all our audience to keep commenting also during the presentation, so that we can immediately start with your questions after the presentation, as we have a very tiny time delay in our recording. So yeah, with that, Deepshikha, I would like to give the floor to you.
Okay. Hello everyone. Thank you so much for this kind introduction. First of all, I would like to thank the organizer and Porous Media Tea Time Talk committee members for providing me with this opportunity to present my work on this great platform. So today I will talk about solid fluid interfacial area measurement for reservoir scale wettability quantification in porous media. So as this topic suggests that I will be going to discuss a way to measure the fluid solid contact area that can predict reservoir scale wettability. So my question is with the audience would be that what is reservoir scale wettability? So before going to discuss about the what is happening, actually excuse me, actually I'm not able to change the slide.
Okay.
So
we do see this slide on the screen. You could, Kamala, do you have any advice? Otherwise, I would suggest to close to minimize the presentation and to check. Is it whether it works when you reopen?
Actually, I think so. I have to close it and then reconnect.
Okay, let's do that then.
Sorry for this inconvenience.
No, that's okay.
Actually, when I have tried it, it was okay all about. But right now, what is going on, I am not getting.
No worries. Let's fix it. Could you share your screen, Deepshikha?
Yeah. So now it is visible.
Yeah. If you can make it, yeah.
Is it okay?
Can you make it full screen, please?
Actually, when I will do it now, then I'm not able to see you guys.
So could you expand it just by dragging it on the left hand side?
Okay.
That should do the job there.
Now it is okay.
You can further expand it, yeah, a little more. Yep, keep going.
Okay, then now let's go ahead. So before going to discuss about the reservoir scale wettability, I would like to tell Now again, what is going on?
If yeah, this looks
okay.
good. Yeah.
So
Yeah.
before going
Fantastic.
to discuss the, yeah, is it okay?
Yes, absolutely.
Okay. So before going to discuss about the reservoir scale, I would like to tell about the wettability. In general, wettability is defined as the ability of a fluid to adhere to a surface. If the fluid is more wetting for a surface, it will try to occupy more surface on the solid. And if the same volume of the fluid is non-wetting for a surface, then it will occupy less surface on a solid. So next question that comes in our mind, that how do we quantify wettability? So there are various methods have been proposed that already being used to quantify the surface wettability, and historically contact angle method is most frequently used as most suitable method for quantifying the surface wettability. And many research with microcity analysis has proved that the contact angle method can be applied in a reservoir pores to quantify wettability. But we are interested to know the reservoir scale wettability. So as we know that in a reservoir, reservoirs are huge, and when we go inside the reservoir, we see grains, and these grains can be water wet, mixed wet, and oil wet. And depending on that, there is also so much heterogeneity inside the reservoir that depends, that is due to the roughness, that because of the chemicals and multiple fluid flow inside the reservoir. Then how do we quantify wettability in a reservoir? By just quantifying the surface area that made by a drop on a flat surface. And particularly in a reservoir, when we are talking about to recover oil, and when we are talking about the groundwater remediation where we want to recover the water, so in these kind of systems wettability play a very significant role, and it affect many other parameters that leading to varied recovery rate by varying the porous media wettability that we have performed in our in our lab also. And here we can see that the water wet reservoir give oil recovery, more oil recovery, and least oil recovery we get in a water wet system. So uh, this was the most challenging and confusing question with which we deal with. And recently developed microcity analysis based approaches shown that the fluid solid interfacial area measurement can discriminate the different wetting conditions more efficiently than the contact angle method. Therefore, by recognizing that more wetting fluid has more interfacial area, we can say that we can quantify the reservoir scale wettability by just quantifying the fluid to solid interfacial area. So now we set out to find a way to discover the reservoir scale wettability by just measuring the fluid solid interfacial area, and for that we will talk about it. So for measuring the fluid solid interfacial area at reservoir scale wettability quantification, we have explored dual tracer method. The dual tracer, in a dual tracer method, we use two tracers for a fluid phase, one ideal tracer and one adsorbing tracer. We use one ideal tracer because it will follow the fluid flow path and tells us about the pore volume available in the reservoir. And adsorbing tracer will dynamically adsorb and dissolve on the solid surface, and and tells us about and it will come delay to arrive at the production point, because of the surface adsorption and desorption of the fluid will take place only on the solid surface of the porous medium. So for measuring the fluid solid interfacial area, we get some delay in an adsorbing tracer, and this delay tells us about this factor, which is Ka NAI divided by Q, where Q is the flow rate, K is the adsorption partition coefficient, and AI is the fluid solid interfacial area. So if we want to quantify this fluid solid interfacial area, we difference these two equations and we get this equation. There is two unknown in this equation, which is Ka and Ai. And for getting Ki, we should know Ka value, that is adsorption partition coefficient for a solid matrix. So it is our first task to measure the. So it is our first task. What is happening again? Estimate the adsorption partition coefficient value. Sorry.
Can we help you?
Yeah, now it is okay.
Okay.
Yeah. To estimate the Ka, we perform the single phase flow experiment at 4 different flow rates in a cylindrical porous medium, which is densely packed with the glass beads as our proxy porous media. And during the single phase flow, at the steady state, we first inject the ideal tracer as the step input and then inject the adsorbing tracer at the same flow rate. And we get slight delay in adsorbing tracer breakthrough curve. This breakthrough curve tells us the mean residence time of the tracer inside the porous medium. And identically, the first movement of the ideal tracer is equal to the theoretical mean residence time. Therefore, we are calculating, we first compare the experimentally calculated mean residence time with the theoretically calculated mean residence time at a 4 different flow rate. And at the same flow rate, we get ideal tracer mean residence time has an excellent match with the theoretical mean residence time. And at the same flow rate, we get the higher mean residence time of the adsorbing tracer. Then this difference in mean residence time gives us Ka by using this equation, because we know Ai here. Because during the single phase flow, the whole solid surface area of the porous medium is being covered by the single fluid only. Now,
I'm afraid we lost Deepshikha. Deepshikha, unfortunately, we cannot hear you anymore, and we also lost your video. And it appears also your screen is still there. Okay, Deepshikha, we will try to solve the issue with you in the background, and in the meantime, move ahead to Catrin Harris. Catrin, can I hand over to you?
Hi. Hi, everyone. My name's Catrin. Can you hear me? All okay? Cool. I'm a second-year PhD student at Imperial College London, and today I'm going to be talking about my project looking at the impact of heterogeneity on CO2 capillary trapping within the Catrin sandstone. So I'm going to be quantifying capillary heterogeneity trapping and discussing the implications on scaling from the core to the field. So I'm looking in the framework of geological carbon storage within saline aquifers. So I'm studying the trapping stage of a CO2 injection and migration project, looking specifically at the imbibition processes that occur at the trailing edge of the CO2 plume. So a challenge for geological carbon storage is ensuring that CO2 is stored securely. CO2 is trapped by a combination of physical and chemical trapping mechanisms, and as shown in the figure on the top right, these contributions vary over time. And these mechanisms are also impacted by the constitutive relationships, such as capillary pressure and relative permeability, as shown in the figure on the left. So we need to understand and be able to effectively model these mechanisms. So I'm interested in the capillary or residual trapping mechanism. So pore scale capillary trapping occurs due to capillary forces and is controlled by snap-off processes. It's a key mechanism underpinning storage security and immobilizing a significant proportion of the CO2 plume. However, there's uncertainty in the trapping associated with this due to geological heterogeneities, and that's what I'm going to discuss today. So natural geological heterogeneities are intrinsic to sedimentary rocks in which carbon sequestration occurs. They impact flume migration and trapping over different length scales, and these introduce uncertainty into current models. So I'm interested in the impact of capillary pressure heterogeneity on capillary trapping. So in order to understand the impact of heterogeneity, our research group carries out experiments at the small scale in order to create models at the larger field scale. So in a carbon sequestration project, CO2 is injected and migrates to the aquifer, giving rise to brine emission at the trailing edge of the CO2 plume. Capillary pressure heterogeneity modifies the distribution of trapped CO2. We see that the CO2 saturation increases behind regions of high capillary entry pressure, trapping CO2 at saturations greater than pore scale residual trapping alone. And this is a consequence of capillary pressure and flux continuity within the system. So on the left-hand side of the screen, I've shown a simple two-region model. So there's an area of low capillary entry pressure below that of high capillary entry pressure, and we're flowing upwards into the system. So what we observe when we model this is on imbibition, CO2 saturations build up behind regions of high capillary entry pressure. And it's this additional mechanism which is referred to as capillary heterogeneity trapping. So I'm going to discuss the importance of capillary heterogeneity trapping, demonstrate within a target field scale storage site. So the case study I'm looking at is the Catrin D sandstone, the Golden Eye Field, which is located in the North Sea. So in order to demonstrate the impact of capillary heterogeneity trapping, I've created 1D decahectometer scale models of the Catrin sandstone based off site-specific experimental data. So this slide just demonstrates the workflow which I followed. I used core and field scale data to build heterogeneous models. I then ran flow simulations on these models and used the results to inform of the best practices when upscaling from core data. So to start with, I discussed the core scale experimental data which I used. So a recent 2020 paper, work carried out by colleagues at Imperial College, details capillary pressure and relative permeability data for the Catrin sandstone, calculated from core flooding experiments. So here on the left, I've demonstrated the experimental drainage capillary pressure data, fitted with the Brooks-Corey model as shown. And on the right-hand side, I've demonstrated the Corey parameterization for the drainage gas and water relative permeability. The gas imbibition relative permeability curve is calculated from the mobile CO2 saturation using standard methods by accounting for CO2 residually trapped. So this is the experimental initial residual saturation relationship. We carried out steady-state core flooding experiments using medical X-ray CT scanning, where at the end of drainage, the core is flooded with 100% brine, and the initial residual saturations are measured. So this provides detailed characterization of residual trapping characteristics over the centimeter scale. And what we find is that the pore scale residually trapped saturation has a first-order dependence on the maximum initial CO2 saturation achieved prior to brine imbibition. So the data has been fitted with the land trapping model, where the average land trapping coefficient is shown to be 1.7. However, you can see this varies between 0.8 and 2.8, and this represents a very large variation in locally trapped CO2. So along with this core scale experimental data, I also used field scale data. So due to its potential as a target UK storage site, there's lots of information online regarding the Captain Sandstone. So in order to create field scale models, I used shell, neutron, wide and log data for porosity versus depth, and the porosity permeability relationship obtained from ArcAl data. So I used both this core scale data and the field scale data in order to create 1D geological models or realizations of the Captain Sandstone. So I used leverage J scaling in order to scale the capillary entry pressure with depth. And this creates vertically heterogeneous 1D models with layered heterogeneities, which are representative of bedding planes. It's the variations of capillary entry pressure with depth that result in capillary heterogeneity trapping. So I then ran numerical flow simulations on these models. And so the model represents a 1D vertical column to the reservoir, where I'm flowing upwards into the domain, perpendicular to the heterogeneities. So CO2 is injected at a constant rate into the bottom of the domain for 2 pore volumes. So the final saturation at the end of drainage is shown on the right-hand side, and it's heterogeneous, and this is due to the capillary entry pressure variations within the system. So we then inject brine into the bottom of the domain to mimic brine imbibition. So from pore scale residual trapping alone, we'd expect to see a residual saturation related to the initial saturation through the land trapping model. Instead, when we run these imbibition simulations, what we find is that the final saturation is greater than that from residual trapping alone, and this is due to the impact of capillary heterogeneities. And these simulations are all ran on CMG IMAX. We can then look at the results we get from these simulations. So I use this equation to quantify the proportion of trapping which is caused by capillary heterogeneities. And we can see from these initial results that the proportion of capillary heterogeneity trapping within the system is a function of rate. So we'll come back to these results. First of all, I want to discuss the main outcome of this work, which was to inform of the implications of extracting particular trapping characteristics from core flood experimental data. So an alternative way to consider the saturation profile for the Captain is as an initial residual saturation plot. Pore scale residually trapped saturations are calculated from the land trapping model as was input into the simulations. Heterogeneity acts to break down this relationship, and deviations from the land trapping model result from capillary heterogeneities, and this may be used to explain the scatter observed in IR core flooding experiments. It has implications for the choice of trapping parameter extracted from experimental data. So if we extract the average trapping parameter, which is commonly taken, this incorporates the impact of capillary heterogeneity trapping and no longer describes the pore scale residual trapping mechanism alone. So I've shown here for 2 different rates, and you can see that the clear impact of rate on capillary heterogeneity trapping. And this indicates if you extract the average trapping parameter, this will also be a function of rate. And so experimental conditions need to be representative of the reservoir. This is the core scale experimental data I showed earlier. So the maximum land trapping parameter 2.8, as shown in the blue curve, I'm going to use this in the simulation. So this has no impact of heterogeneities at this scale. So I've run the simulations using both the average, C is 1.7, and maximum, C is 2.8, land trapping parameters from experiment. And it's observed, sorry. What was I going to say? Oh yeah, so I've overlaid here the core scale experimental data, and it's observed that modelling the field scale Captain Sandstone system with the maximum land trapping parameter 2.8, as shown on the right-hand side, results in a better overlap with the core plug experimental data. And this suggests extracting the maximum trapping parameter rather than the average, which is typically used from experimental data, may be more appropriate for use in numerical simulators, such as CMG IMAX, which also capture the impact of heterogeneities on top of pore scale residual trapping. So I then ran, as I said, the workflow with both the maximum and the average land trapping parameter. And these are the results. And what we find is by modelling the system with the maximum experimental land trapping parameter, we find that capillary heterogeneity trapping may account for a larger proportion of trapping in the system. So we see approximately double compared to when the average trapping parameter was used. And this shows that the impact of capillary heterogeneity trapping might actually be greater than originally assumed in some models. So just to quickly conclude, I ran flow simulations of heterogeneous Catrin sandstone models to quantify the proportion of capillary heterogeneity trapping. I demonstrated deviations from traditional poor-scale residual trapping models, consequence of capillary heterogeneity trapping. And I've shown that the results from field-scale models can be linked back to core-scale data, helping to inform on best practices from core-scale data analysis. So I want to thank you for listening, and if you have any questions, please ask, or there's an email on the slide if you'd like to get in contact at a later date. Thank you.
Thanks for that talk, Kat. It was really great. Yeah, so if anyone has any comments or questions, if you just type them into YouTube, then I'll read them out. I have a first question, and I'm actually just really interested if you have, like, how are you planning to upscale your findings? You mentioned it on the last slide. I just was wondering if you had more insight into that.
Yeah, we've been having some thoughts about this. And so looking at different, so this is all in 1D, and looking at 2D, 3D, it will be different. So at the moment, we're just thinking about, we can go from the core scale data, what might be best in order to put into field scale models. But then going to a larger scale, what I'm looking at the moment is a best way to average the land trapping parameter using sort of upscale saturations, or is it better to use sort of like mean trapping parameter based on the different grid cells? So that's something I'm looking at the moment. And then in higher dimensions, we're looking at using invasion percolation in order to try to look at these effects. So it's a work in progress. Thank you.
It would be interesting to see. Do you think as well, like the capillary heterogeneity is so extreme that you will use it to choose your locations, or do you think it's just something that we need to model once we've chosen a location to basically be like, this is how much we're going to trap and this is how great the sweep of the CO2 injection is going to be? Or do you think it needs to come into the planning stage of choosing a site?
Yeah, I'm not sure, but so for example, when you see sort of discrepancies between models and prediction and actual real life settings, so something like at Sleipner, where you see the differentiation, so they made all these models and predictions, and we see this sort of pooling beneath the layers of layered heterogeneities. So I don't necessarily know whether it would come into the planning stage, but it's really important in terms of like regulations. So if you make a model, it needs to sort of like match what's actually going to happen. And so I think it will definitely needs to be incorporated in models in order to sort of like better comply with regulations, to have models that will represent what actually happens at the field scale. But I don't know if necessarily it will determine the storage site per se.
Great, I've got a question here. Let me just bring it up. It's from Martin Blunt. He says, fascinating work. Could you use a large-scale invasion percolation model for 3D simulations as developed by Yortis? Yeah,
this is exactly something that I'm starting on now. It's a long work in progress, I think. But yeah, it's exactly in the research group, we're going to do some work on the endurance field and scaling that up in a 3D model. So that's the next part of my PhD. Is basically doing this.
Great. Do I have any questions from the my other co-presenters? Great. So thank you for your talk. And yeah, if anyone has any questions, they're more than welcome to email you as well, which is great. We have lost Deepshikha. Nothing like the live theatre, I guess. So we will move to closing the session. And our next session is on the 18th of May at 3 p.m. Central European time. So make sure you subscribe to our channel so you get these notifications. And with that, I would like to say thank you for our audience and thank you to our speaker from today. We are a big team now and we very much appreciate your support. So thank you.
I would like just to add that we didn't forget Deepshikha, of course, in our future session. So we will re-invite her. So everybody who was keen for her presentation. We're gonna stream it as well. Thanks.